So we've been talking about functions of 2 and 3 variables, and we've spent a lot of time talking about the derivative concept. And so the derivative concept, if you have a function of 2 variables, then we've said that the derivative is this thing called the gradient, which is a vector who consists of 2 different partial derivatives. Essentially, one variable derivatives where we treat the other variable as a constant. So now what we'd like to ask is whether or not there's a decent integral concept for a function of 2 variables. If we have f of xy, then what's the right integral concept? Moreover, is it possible that this integration concept is somehow done in such a way so that we integrate, treating one of the inputs as a variable and the other as a constant in either one of the 2 directions? Is it possible to do this? That's the topic for the day. Now, in order to start to motivate this concept, let's go back and remember how we did it in Calc 1. Let's go back to one variables, functions. So suppose we had a function y equals f of x. Well, given a function like the one we see up here, we had an integration concept. We integrated such a function with respect to the variable x over an interval. And what this represented was we would take the domain of the function. We would look at a small interval inside that domain, the interval from a to b, and then this integral would represent the signed area of the region between the x-axis and the curve of the function. How we actually went around and built this particular integral, how we computed it, was we would take the interval and we would chop it up into a number of skinny subdivisions of width delta x. For each one of these subdivisions, what we would do is we would pick a point inside that interval, say the point x1. We would find the corresponding y value connected to that point, which is f of x1, and then we would draw a rectangle and compute the area of this first rectangle. So the area of the first rectangle would be f of x1 times the width delta x. Then we'd go to the second interval, find another sample point, say x2, find the y value connected to that point, which would be f of x2, and then using that y value and the width, we would draw another rectangle and compute its area, which would be f of x2, the height, times delta x, the width. And then we would repeat it one last time, in this case, because we only have 3. Find a third sample point, find the function value of that sample point, turn that into a rectangle, compute its area. If we had more rectangles, say n of them, we'd keep going until we got to the nth subdivision. We could condense this long expression using summation notation as the summation of f of xi delta x, where I goes from 1 to n, where n is the number of subdivisions. This kind of a beast was called a Riemann sum. It was sometimes denoted as Sn of f, the Riemann sum with n subintervals of the function f. And so the basic idea was that every Riemann sum was an approximation of this volume. The approximation improved the more rectangles we used. And so if we took a limit as the number of rectangles went to infinity, this limiting value was called the definite integral from a to b. And so that was our integration concept from Calc 1. So how much of this would carry over to a function of 2 variables? So let's consider a function of 2 variables. Geometrically, we know that the graph of something like this would be some sort of a surface. So let's imagine that we had some kind of a big giant surface floating around right up here. So we want to go and generalize the concept from 1 variables to 2 variables. So the first thing we needed was we need the idea of the interval we're going to integrate over. Well, this is a 2-dimensional function, and so the simplest 2-dimensional object in the xy plane would be a rectangle, something like this. So this would be a rectangle whose, say, goes between the x values of a and b and the y values of c and d. Such a rectangle is sometimes denoted as AB cross CD. This isn't the vector cross product, it's just using the same sort of notation. So given a rectangle like this, then we could talk about the portion between the rectangle and the part on the surface of the graph. So I'll find where each of these points are on the graph. On the graph, we're going to have some sort of a shape that's probably a little wobbly and bendy like this. And we could take a look at the region between the graph and the xy plane over this rectangle. So let's ignore the rest of the surface and just focus on this shape. We'd have a region whose shape is something like this. Now, in the one-dimensional case, we looked at the area of the two-dimensional figure we got. Well, this is a three-dimensional figure, so it makes sense that what we should focus our attention on is the volume of this. And so this is going to be the integration concept we want to work with. So this is going to be what our integral of f of xy is. And right now I'm going to put this in quotes because I haven't quite figured out what the notation is going to be. And our key to figuring out what the notation is going to be is to ask, how would we work this out? How did we do it in one variable? Well, in one variable, what we did was we took the region we were integrating over, the interval xy, and we chopped it up into smaller intervals. So we're going to do the same thing here. We're going to take this rectangle and we're going to chop it up into smaller rectangles. So let's say we chop it up like so. So I'm going to take the rectangle and I'm going to chop it up so that each one of its horizontal pieces has a width of delta x, and each one of its vertical pieces has a width of delta y. So in this case, I've got 3 delta y's and 5 delta x's. And there's no reason that I have to use the same number of subdivisions on both the x and the y values. I'm just going to slice them up into small rectangles. Now, what am I going to do with this? Well, for each one of these rectangles, I'll take a sample point on the inside. Say, let's call this first sample point right here, x1, y1. I'll go and I'll put this, find the output value right here. That would be f of x1, y1. And then, just like we did in the one variable case, instead of treating it as a curved thing, I'll treat this as simply a flat height. Connect it back down to my base, and I'll have a single rectangle here. We can compute the volume of this rectangular piece by using the formula base times width times height. Now, the length of this rectangle is delta x, its width is delta y, and its height would be, well, how tall it is, that's the height f of x1, y1. So that would represent the volume of the very first rectangle. Then I'll go and do the same thing we did in the one variable case. I'll go to the next subrectangle. I'll find another little point here. So this will be x2, y2. I'll find where that point is up here on the surface someplace, say this part right here. I will approximate the graph not as being curved anymore, but by being a horizontal flat plane piece exactly at that height. And then I will connect this rectangle down to that tiny subdivision, and that's going to give me a second approximating rectangle, like so. And then we can compute the volume of this rectangle. The volume of this rectangle will be the length of its base, delta x, the width of its base, delta y, and then the height of this rectangle, which would be f of x2, y2. And then I'll add this to the other one. And so I'll keep doing that. At each rectangle, I'll find a sample point. This is x3, y3. I'll find the height of that point on the surface. I will replace the curved part of the graph with a flat rectangle at the very, very same height. I will then use this flat part as the top of another rectangle, work out the volume of this rectangle, base times width times height, and then add it to the previous mix. And then I want to keep going. In this case, I'm going to have to do this a grand total of 15 times. I will tally up all of this work together, tally up the heights of each one of these rectangles. And so if I go and invoke the summation notation, that means I'm going to be doing this. We will be summing up f of xi, yi, delta x, delta y. We're summing this over the m delta x divisions and the n delta y divisions. Something like this will be called a Riemann sum, like we did before. And the notation is sometimes S of m n f. So a Riemann sum where we use m subdivisions in x, n subdivisions in y of the function f. And so what are we going to do to make an integral out of this? What we did in Calc 1 was we would take any one of these Riemann sums, which was an approximation of the volume, and then we would take the limit as the number of these subdivisions got bigger and bigger and bigger. So we're going to take the limit as m and n get larger and larger and larger. And this limit is what we're going to call a double integral for the function. So the double integral over the rectangle of the function f of xy. Notice that in our formula right here, the delta x, delta y, that just represents essentially the area of the base of the rectangle in each one of these approximations. And so, as a reminder that we're essentially measuring height times the area of the base, we're going to use the symbol dA to denote an object like this. So there's a couple bits of notation right here. So the R, this is this rectangle, the AB cross CD. This part right here is simply a reminder that this is a two-variable function. So we have a double integral. There was two parts to this. This is supposed to be the reminder of the delta x and the delta y subdivisions. As for this notation right here, well, you might remember in Calc 1 that each one of these integral signs is supposed to represent a sum. So we are summing up heights of a rectangle times the area of the base. But the area of the base is very, very small, and that's what the little d is. So this whole symbol is supposed to tell me a large story. We're doing a two-variable sum of heights times tiny bases over a rectangle. And so this is going to be our starting integration concept. A double integral over a rectangle. Approximate the double integral over the rectangle 0, 1 by 0, 1 of the function x squared plus 1/3 y dA with the Riemann sum S33. So what's being asked here? Well, we've got this function, z equals x squared plus 1/3 y. This defines some surface in the three-dimensional xyz space. In the xy plane, we're going to look at this rectangle who goes from 0 to 1 in the x direction and 0 to 1 in the y direction. So we're going to be looking at this square cornered right here in the first octant. Every point on this square corresponds to a specific point on the graph. So for example, this point corresponds to a point right here, this point corresponds to a point right here, this point to a point right here. And so, between the surface of the graph and the xy plane, we have a three-dimensional region. Now, the volume of this region is exactly what this object is supposed to represent, this double integral. Since it's not a rectangle, the top is all curvy up here. I can't go and compute its volume directly. And so the problem is not asking us to compute its volume exactly, but to approximate it with a Riemann sum. In other words, we're going to go and approximate the volume of this object by adding up the volumes of rectangles. This first 3 in S33 in the Riemann sum means we're going to take the x part, the horizontal part of this rectangle, and slice it up into 3 subdivisions. The second 3 means we're going to take the y component, or the vertical part of this rectangle, and slice it into 3 pieces. And then we're going to do exactly what we saw on the previous picture. In each one of these rectangles, we will take a sample point, say this point right here. We'll find where that sample point goes up on the function, right here. And then instead of using the curved surface of the function, we'll replace it with a completely flat piece at exactly that height. And then we'll compute the volume of the rectangle formed by this flat piece and the base. And then we'll simply repeat for each new point. We'll take a sample point here, use its height to flatten out the curved part of the surface up top, compute the volume of this rectangle, and then repeat 6 more times to get a grand total of 9 subrectangles. To do this work by hand, it might be easiest for us to go and draw what this domain is carefully. In this case, it was a square that was 1 unit long by 1 unit long, centered or with its lower corner at the origin. We subdivided the horizontal component of this rectangle into 3 even pieces, which means each of these subdivisions is happening at a third away across. We also took it vertically and subdivided it into 3 pieces vertically. So again, those should happen at subdivisions of a third. And we're going to go and pick sample points. So for example, the green rectangle corresponded to picking a sample point in this first chunk right here. Now to make my life easier, I'm simply going to pick the midpoint each time. So I'll pick the first midpoint would be right here. The second midpoint, the orange rectangle I've shown, will be right there. And then every other point, I will simply pick the midpoint each time. And it doesn't matter what point we pick. Each point will give us a slightly different approximation, but we want to pick something consistent. This is kind of like in Calc 1, the idea of using the left-hand rule or the right-hand rule or the midpoint rule. This would be the two-dimensional analog of the midpoint rule. Now notice that each one of these midpoints happens exactly between 0 and 1/3, which means this happens at a sixth. 1/3 is 2/6, so this next point should be at 3/6. This subdivision is at 4/6, so this point is at 5/6, and then 6/6 is 1. I can kind of easily describe where each of these points happens, and then I can start working out what each of these values are. So for this first rectangle, the sample point we're going to pick is the point 1/6, 1/6. The height of that rectangle will then be f of 1/6, 1/6, which in this case would be 1/6 squared plus 1/3 times 1/6. So that'll get me 1/36 plus 1/18. And 1/18 is just 2/36. And so this will give me a grand total of 3/36. That's the height of the first rectangle. Its base is going to be 1/3 of a unit long by 1/3 of a unit tall. And so that's going to give me a grand total of 3 over 36 times 9, 3/24. That would be the volume of this very first rectangle right here, 3/324. Moving on to the second point. The second point is the point 3/6, 1/6. That's my second sample point. We plug it into the function, we'll find the height of the rectangle. In this case, it would be 3/6 squared plus 1/3 times 1/6. That would be 9/36 plus 1/18, which is 2/36. And that gives me a grand total of 11/36. That's the height of the second rectangle. The base of that second rectangle has a base of 1/3 and a width of 1/3. And so that will give me a grand total of 11/324. That would be the volume of this orange rectangle that we've drawn. I could then move on to this third point, which is 5/6, 1/6. Plug it into the function, we'll find the height of the rectangle. That would be 5/6 squared plus 1/3 times 1/6, or 25/36 plus 1/18, or 2/36, which would give me a grand total of 27/36. That's the height of what would have been the third rectangle, the purple rectangle I would have drawn right here, if I had gone through all of the details. The base of it, well, its length is a third and its width is a third, and so that will give me a grand total of 27/324. And so we've added up all of the rectangles on the bottom row. We could repeat this for each of the remaining 6 points. If we complete the exact same process with the remaining 6 squares, we'd find along the middle row these light blue rectangles who correspond to these light blue volumes here, and these dark blue rectangles in the back row who would correspond to these dark blue volumes here. And so if we were to take all of these volumes and add them up, then we would get a grand total of 159 324ths. We could divide everything through by 3, I guess, and reduce this thing down to 53 108ths, which is pretty close to a half. In fact, according to a calculator, this is approximately 0.49. So there's approximately a half a cubic unit of volume underneath this surface over this particular rectangle. This example shows a couple of things. One, the basic premise behind a double integral is exactly the same as the basic premise behind a definite integral. You add up a lot of things. This also means it has the exact same disadvantage as a Riemann sum. We do lots and lots and lots of calculations. So is there any way that we could use a fundamental theorem type thing to make our life a little bit easier? Well, it turns out that the answer is yes. So let's go back to taking a look at this double integral. So the volume of this object right here is going to be the double integral over the rectangle AB times CD of the function f of x, y, dA. That's the symbol we're using for this particular volume right here. Now, one of the ways we could do it is just like last time, we can slice it up into rectangles. But is there a more efficient way of computing its volume? Well, imagine taking this three-dimensional object and slicing it like a loaf of bread. So we'll slice it down through the shape over and over and over again. Something like this. Well then, the volume of this shape, this volume right here, could be approximated by adding up each of the thin wafers. We could take this wafer right here, plus the wafer behind it, plus the wafer behind that one. We could keep adding up each one of those wafers. Now, each one of these wafers has a width of delta y. As long as we know what the area of the face of this wafer is, then its volume is always going to be the area of the face times the thickness of it. That's one of our basic formulas from Calc 1 or geometry. But what is the area of this piece right here? Well, let's isolate one of these particular slices. Now let's say that this particular slice happens to be centered at the y value y0. So the thickness of this slice is delta y, because that's how we sliced the object. What about the area of the face? Well, let me look at it straight down the y-axis. So what I would see here is I would see A and B on the x-axis. I would see a flat bottom, 2 flat sides, and then a curved top. The equation of this curved top would be z is equal to f of x, y0. Y0 here is going to be a constant because I'm keeping it fixed in this one slice. And so I'm looking at the area below this shape, but above what would be the x-axis between A and B. So the area of this face is just going to be the integral from A to B of f of x, y0 dx, a single variable integral. So in my picture right here, the area of this first face would be the integral from A to B of f of x, y1 dx. This would be the integral from A to B of f of x, y2 dx. This would be the integral from A to B of f of x, y3 dx. We've now figured out a formula for the area of each one of these faces. So if we add them up, we would get that the volume is approximately the sum of the areas of each one of the faces, the integral of from a to b of f of x yi dx times the thickness of each wafer, delta y, and we would do that for the n subdivisions delta y. Well, that's the approximation of the volume. If I wanted to make the volume exact, then we would take a limit. We have the limit as n goes to infinity of the summation I going from 1 to n of some formula involving y, delta y. That's exactly the Calc 1 definition of the integral from c to d dy of this function of y. What function is it? Well, it's the function, the integral from a to b of f of x, comma, y dx. And so we found a new formula for the volume of this object. Let me summarize that. We've just shown that the double integral over a rectangle of the form AB cross CD of some function f of x, y, dA can be thought of as taking the integral from c to d of the integral from a to b of f of x, y, dx, dy. This is sometimes called an iterated integral, because what we're doing is we're first working out an integral with respect to x, that was the area of each of those wafers, and then we're going to work out an integral with respect to y. We're going to stack up those wafers. I'll point out that if we had repeated the exact same argument but sliced that volume a different way, we could have expressed this as the integral from c to d of f of x, y, dy. Those would have been the areas of faces stacked vertically, and then we could have integrated that from a to b dx. And so this is what's known as Fubini's formula. And it allows us to work out a double integral by treating them as what's called iterated integrals, which just means it's one single variable integral stacked inside of another one. To see how this idea gets used in practice, let's go back and take a look at the example we did before. Let's evaluate the double integral over the rectangle 0, 1 by 0, 1 of x squared plus 1/3 y dA. So Fubini's theorem says that this double integral could be expressed as follows. What we could do is we could take the function, and we'll first integrate it with respect to x between the limits for the x value 0, 1, and then we'll take that and we'll integrate that as a function of y between the limits on the y value 0, 1. So let's go and do this. Let me sort of focus first on the part on the inside here. The integral from 0 to 1 of x squared plus 1/3 y dx. So remember, in a process like this, we're thinking of y as being a constant. So this is an awful lot like the idea of doing a partial derivative. This is now sort of a partial integral. So using the fundamental theorem, we would just come up with an antiderivative of x squared plus 1/3 y dx, and then we'll evaluate it between x equals 0 and x equals 1. So how would we find an antiderivative? Well, the antiderivative of x squared is 1/3 x cubed. What about an antiderivative of 1/3 y? Well, just think y is a constant. So the integral of a constant is just the constant times x. And so we'd have 1/3 y x evaluated from x equals 0 to x equals 1. So now let's plug those values in. If we plug in x equals 1, we're going to get 1/3 times 1 cubed plus 1/3 times y times 1. If we plug in x equals 0, we're going to get 0 plus 0. So this gives me a grand total of 1/3 plus 1/3 y. That's the iterated integral, the inside part, the area of a face of a wafer at a specific y value. Now what I'm going to do is I'm going to take this y value and plug it back into here. We've worked out the area on the integral on the inside. And so this is going to give me the integral from 0 to 1 dy of 1/3 plus 1/3 y. We've worked out the inside integral and found that it's 1/3 plus 1/3 y. Well, now I have a brand new fundamental theorem of calculus problem. We need to find an antiderivative of 1/3 plus 1/3 y dy, and then evaluate that from y goes to 0 to y goes to 1. So let me get myself some new space. If we integrate this, the antiderivative of 1/3 is 1/3 y. The antiderivative of 1/3 y would be 1/3 times 1/2 y squared, evaluated from y equals 0 to y equals 1. So if we plug in 1, we're going to get 1/3 times y plus 1/3 times 1/2, or 1/6 times 1 squared. If we plug in 0, we're going to get 0 plus 0. So that gives me a grand total of 1/3 plus 1/6, or, let's see, that would be 2/6 plus 1/6, which is 3/6, or a half. You might remember that when we did this problem before, we knew already that the volume was approximately 0.49. And so a half is pretty consistent with that, but now a half is the exact value. Now it's worth pointing out, though, that Fubini's theorem says that we could have also worked out this integral, this double integral, by taking the function x squared plus 1/3 y and integrating it with respect to the y variable first, between 0 and 1, and then taking this and integrating it with respect to x between 0 and 1. And we're supposed to get the same answer. Well, let's see if that actually works. So the first thing I'm going to do is focus on just that integral on the inside, the integral from 0 to 1 of x squared plus 1/3 y dy. And so according to the fundamental theorem of calculus, all we need to do is cook up an antiderivative of x squared plus 1/3 y dy, and then evaluate that between y equals 0 and y equals 1. So if we integrate this expression with respect to y, x squared is a constant, so the integral of a constant is just multiplied by y, and the antiderivative of 1/3 y would be 1/6 y squared. So we'll evaluate that between y equals 0 and y equals 1. When we plug in 1, we're going to get x squared times 1. When we plug in 1 on the second piece, we'll get a 1/6. Then we'll plug in 0, we're going to get 0 plus 0. So that cancels with x squared plus 1/6 as the expression inside. So then we will go and integrate from 0 to 1 dx, x squared plus 1/6. So using the fundamental theorem of calculus, an antiderivative of x squared is 1/3 x cubed. An antiderivative of 1/6 is 1/6x, and we'll evaluate that from 0 to 1. So when we plug in 1, we're going to get 1/3 plus 1/6. When we plug in 0, we're going to get 0 plus 0, and a third plus a sixth is a half. So in fact, both of these iterated integrals gave me the correct value. Compute the double integral over the region R of x plus 2y dA if R is the rectangle 1, 3 by 0, 2. So let's just apply Fubini's theorem to this. One of the ways we could compute this double integral is to take the function x plus 2y and integrate it with respect to x first. Now, since the x values correspond to the first part, we would be integrating that between 1 and 3. Then once we have this integral worked out, we can integrate it again with respect to y. Since this part corresponds to the y values, we do the second integral between 0 and 2. So let's work out this particular integration. I'll start off with the inside piece first. That's going to be the integral from 1 to 3 of x plus 2y dx. So we'll find an antiderivative of x plus 2y with respect to x first, and then evaluate that from x equals 0 to from x equals 1 to x equals 3. So an antiderivative of this, well, to integrate x with respect to x, we get 1/2 x squared. To integrate 2y with respect to x, well, that's just a variable, so our constant will tack on the variable x, and then we'll evaluate that from x equals 1 to x equals 3. So if we do that, when we plug in x equals 3, we're going to get 1/2 times 9, or 9/2, plus 2 times y times 3, or 6y. When we plug in 1, we're going to get 1/2 plus 2 times y times 1. So when we do that, we're going to get 9/2 minus 1/2, that's 8/2 or 4, and then 6y minus 2y, which is 4y. So we've now worked out the expression on the inside of the integral. So now we can go back and complete the double integral. That's going to be the integral from 0 to 2 of the expression 4 plus 4y dy. So we'll dig up an antiderivative of this and then evaluate it from y equals 0 to y equals 2. An antiderivative of 4 with respect to y is 4y, and an antiderivative of 4y would be 2y squared. So then we'll plug in y equals 2, we'll get 8 plus 8. Then we'll plug in 0, we'll get 0 plus 0, and that gives me a grand total of 16. So the double integral of this is equal to 16. However, just for comparison purposes, we could have attacked this a different way. We could have instead taken the function x plus 2y and integrated it with respect to y first, integrating it between 0 and 2. Then we could have taken that value and integrated it with respect to x between 1 and 3. So how would this have shaped up? Well, let's first focus on the integral on the inside. The integral from 0 to 2 of x plus 2y dy. Well, we'll find an antiderivative and then evaluate that between y equals 0 to y equals 2. An antiderivative of x plus 2y with respect to y would be xy plus y squared. If we plug in y equals 2, we're going to get 2 times x plus 2 squared. If we plug in 0, we're just going to get 0 plus 0. And so that will give us 2x plus 4 as the inside expression on the iterated integral. So that means that the double integral is now the integral from 1 to 3 of 2x plus 4 dx. So we can use the fundamental theorem again. We'll integrate this with respect to x, and then plug in x equals 1 and x equals 3. The antiderivative of 2x would just be x squared. The antiderivative of 4 would be 4x. So then if we go and plug in our values, when x is equal to 3, we're going to get 3 squared, which is 9, plus 4 times 3, which is 12. When we plug in x equals 1, we're going to get 1 plus 4. So that'll give us a grand total of 21 minus 5, which is 16 again. So this double integral is 16 no matter how we slice it. Compute the double integral of the function x e to the xy dA over the region R, where R is the set where 0 is less than or equal to x is less than or equal to 1, and 1 is less than or equal to y is less than or equal to 2. So the first things first is let's try to figure out what this region R actually is. If I were to try to sketch it, it has sort of two statements in it. One is that x stays between 0 and 1. So here's x equals 0, here's x equals 1, and we're told that the x values stay between these. There's a second statement that says that 1 is less than or equal to y is less than or equal to 2. So here's y equals 1, here's y equals 2, and it says that all of the y values stay between these 2 points right here. And so if I look at the points, or the places where both of those conditions are met, I see that I'm actually describing this rectangle right here. The rectangle 0, 1 by 1, 2. So since this is a rectangle, we can apply Fubini's theorem. And so the double integral over the region R can be expressed as an iterated integral. We could take the function x e to the xy, and we could integrate it, say with respect to x first, between 0 and 1, and then we could integrate that with respect to y, with y going between 1 and 2. So let's take a look at this thing. Let's focus our attention on the expression on the inside first. So the integral from 0 to 1 of x e to the xy dx. According to the fundamental theorem of calculus, this would be the antiderivative of x e to the xy with respect to x evaluated from x equals 0 to x equals 1. So how would we antidifferentiate something like this? Well, it's x times e to a constant times x, and that means it's a great candidate for integration by parts. So if we use the tabular method, where we have a derivative column and an integration column, I'll let the derivative be x and the integral be e to the yx. One derivative of x would be 1, whereas the antiderivative of e to the kx is 1 over k times e to the kx, where k is any constant, in this case y. One more derivative gets me a 0, one more antiderivative gets me 1 over y squared e to the yx, and then I can put on my diagonal entries, a horizontal, plus, minus, plus the integral. And so that tells me that the antiderivative of this function is equal to x times 1 over y e to the yx, minus 1 times 1 over y squared e to the yx, plus the integral of 0 times something else. Well, the integral of 0 is just 0. And so we get x over y e to the xy minus 1 over y squared e to the xy, evaluated from x equals 0 to x equals 1. If we plug in x equals 1, we're going to get 1 over y times e to the 1 times y, minus 1 over y squared times e to the 1 times y. If we plug in 0, we're going to get 0 minus 1 over y squared times e to the 0, which is 1. And so that gets us a grand total of 1 over y e to the y minus 1 over y squared e to the y minus negative 1 over y squared. And so that's the inside of our iterated integral. And so we're going to go and integrate from 1 to 2 the expression y to the minus 1 e to the y minus y to the minus 2 e to the y plus y to the minus 2 dy. So let's do that next. Since this integral has been prepped, it might be reasonable to break it apart into its separate pieces. Minus 1 e to the y dy minus the integral from 1 to 2 of y to the minus 2 e to the y dy plus the integral from 1 to 2 y to the minus 2 dy. Now this last integral right here is pretty easy to integrate. It integrates to negative y to the minus 1, evaluated from y equals 1 to y equals 2. That will get me negative 2 to the minus 1 minus negative 1 to the minus 1, or 1 minus 1 half, which is a half. This bit right here is going to be less friendly. If I look at it, it's y to a power times e to something. So that would make it a good candidate for another integration by parts. So let's do the integration by parts. We'll let our derivative column be y to the minus 1, and we'll let our integration column be e to the y. So if we differentiate this once, we're going to get minus 1 to the minus 2. If we integrate this once, we're going to get e to the y. And this is going to be a problem, because if we keep differentiating, the next derivative would be 2 e to the, or y to the minus 3, and then negative 6 y to the minus 4. This column is getting worse and worse and worse. And so the usual rule is the minute it gets worse, let's just stop it and see what we get. So we're going to do 1 plus 1 minus and an integral. And so that tells me that the antiderivative of y to the minus 1 e to the y dy is going to be positive y to the minus 1 e to the y minus negative the integral of y to the minus 2 times e to the y dy. And then we'll evaluate this from 1 to 2. Now this bit right here, if I plug in y equals 2, we're going to have 2 to the minus 1 times e squared minus, when I plug in 1, I'll have 1 to the minus 1 times e, which means I have e squared over 2 minus e. But this part right here, now I have to go and work out the integral from 1 to 2 of y to the minus 2 e to the y dy. Cool thing is that this part right here, which I haven't worked out, is exactly the opposite of this part right here. And so these two things will cancel. Kind of by dumb luck. And so what I get is, I get the first integral contributes e squared over 2 minus e, plus a term which is canceled by the next term, and the last integral contributes a half. And so this tells me that this double integral is equal to e squared over 2 minus e minus 1 half. That was horrifying. Would it have been any better if we'd looked at the other direction? If we tried doing the iterated integrals in the other way? Well, let's see. Instead of integrating x first, what would have happened if we'd integrated y between 1 and 2, and then followed it up with the integral of x between 0 and 1? How would this have changed things? So now the first iterated integral I have to work with is this one right here, the integral from 1 to 2 of x e to the xy dy. According to the fundamental theorem of calculus, we'd first dig up an antiderivative of x e to the xy dy, and then evaluate that from y going from 1 to y going to 2. Now, the x is a constant. It's going to come along for the ride. And the integral of e to the ky is 1 over k, the constant, times e to the ky. And so in this case, these two guys cancel, and we're just left with e to the xy evaluated from y equals 1 to y equals 2. So that means we have e to the x times 2 minus e to the x times 1, or e to the 2x minus e to the x. And so that's my inside integral, the piece who belongs here. So now we do the iteration. Next we'll integrate from 0 to 1 this expression, e to the 2x minus e to the x dx. So let's work out this integral. We can split this one apart into two pieces. The integral of e to the 2x dx, evaluate from 0 to 1, minus the integral from 0 to 1 of e to the x dx. And then we can use our integration formulas. The integral of e to the kx is 1 over k times e to the kx, evaluated from 0 to 1. And then the integral of e to the x, is e to the x, evaluated from 0 to 1. So when we plug in our 1, we're going to have 1/2 e squared minus, when we plug in 0, we'll have 1/2 e to the 0, minus, when we plug in x equals 1, we'll have e. When we plug in x equals 0, we'll have 1. And so that gets us a grand total of 1/2 e squared minus 1/2 minus e minus negative 1. Or e squared over 2 minus e, and 1 minus 1/2 is positive 1/2. Oops, I copied this thing down wrong. That was supposed to be a +1. I just caught that. And so, thankfully, these two values match up. Now, the point of this particular problem is to show you, first off, that Fubini's theorem always works. The two integrals will always give you the same value, assuming you actually copy the symbols down correctly. But the other part is that this second approach was significantly easier. So always, always, always take a look at the two different iterated integrals you might get. If one of them is giving you trouble, just pause for a second and try the next one out. Very often, one of them is easier, especially if the other one is significantly difficult.